So just in case if you're here and you're not in senior 5, just know that you're in the wrong class. And in case you're in senior 5 and you're also not offering chemistry, same thing applies to you. You are still in the wrong class. So today we shall continue from where we stopped. That was in our last lesson. But before we do that, we need someone to give us an opening prayer. We need to invite God amidst ourselves so that we can have a smooth running of our lesson. I'm going to pick one of those people with their names. I don't know whether we have someone called Infinix or Tekken or C3. Let's rename our devices, please. So I'm going to pick yes, Joshua.
Humble yourselves and we pray. Lord, Heavenly Father, I want to thank you for this great time you have provided to us. You have protected us in our homes with our parents amid this novel coronavirus. So we pray as we start this lesson, give our teacher the knowledge from above, such that we may all get what is right, and let what we learn today, let it stick to our minds until we meet our final examination. I thank you in the name of Jesus Christ. I've prayed.
Amen.
Amen.
So thank you, Joshua, for that prayer. Okay, so I welcome you back once again to our this afternoon lesson. So I don't know whether if there is anybody who still remembers what we discussed last time. Anybody who still remembers what we looked at in our lesson, the first lesson, this second phase. Josh, I don't know whether your hand is still up or you just forgot to lower it. Anybody who still remembers what we discussed? Yes, Joshua?
Yes, teacher, we are discussing about the transitional elements.
We discussed about transition elements. Thank you. Emmanuel, you can tell us some examples of those transition elements.
We looked at transition elements, for example, let me say zinc, we have chromium, we have vanadium. That's all.
Okay, thank you. Then can we have someone define for us what a transitional metal is? How can we define a transition metal? How can we define a transition metal? By show of hands, yes, Gift, I'm seeing 1 or 2 hands. Gift, yes, please.
A transition metal is an element which forms at least one stable ion which partitionally fills 3d orbitals.
Okay, thank you, but something small is missing. In your answer, but thank you for trying. Another person? I want to see some new hands. I hope everyone has got that option of raising up the hand. Yes, Nabudo. Nabudo, unmute.
A transitional metal is defined as transitional metal is defined as an element having a partially filled 3D
I beg your pardon.
I said a transitional metal is defined as an element having a partially filled 3D surface.
Okay, thank you, Nabudo. Thank you for trying. Emerald.
A transition element, these are elements with partially filled 3D partially filled D or F subshells in at least one of the oxidation states.
Okay, thank you. So when we are looking at these transition metals, we look at even the F block elements as well as the D block elements. So like the way he said it, that is an element with a partially filled D or F subshell or sub-energy level in at least one of their oxidation states. Then from there, how can we define a D block element? How can we define a D block element? A new hand, let's see, a new hand, please. Everyone has got that option of raising up the hand. Here I'm now getting to know those who saw the notes. So apart from Manuel and Joshua, who else can give us the answer? How can we define a D block element? How can we define a D block element? It's the time to write your record. Remember, our lesson is live on YouTube. So the moment I pick you and you don't say anything, it will be on record. Even after 10 years, we shall get to remember you. When you contest to become an NMP, we shall say that one time you refused to say something in class. How about when you go into the parliament? So let's take the opportunity. Yes, Arthur?
D block elements, these are elements with partially filled D subshells in at least one of their oxidation states.
Okay, a D block element is that one with a partially D subshell in one of their oxidation states. Then from there we can also define an F block element. An F block element. An F block element. We can have there is someone here called Robert. Judith Robert. What do you think? Remember, when I choose you, your name is displayed alone on the screen on YouTube, so people get to know you. Yes, Judith, Robert. Judith, what do you think? What do you think is an F block element?
Actually, sir, we can't see you.
Yes, I've not shared my screen. We are still reminding ourselves. I haven't shown anything on the screen. So Judith, I'm still waiting for your answer. Apparently, they haven't shown anything on the screen. They haven't shared my screen, so that's why you see a black screen. Okay, any person? Let's go with people who are reading. Any person that could define for us an F block element? Any person? If you're having Infinix Note 6, can you rename your device? And even that person with a Tekno BC3. Okay, Deborah, what do you think?
F block elements are elements with partially filled F subshells in at least one of their oxidation states.
Thank you so much. I'll be one of your references when you want to go to the parliament, in case you want to go there. Thank you for that answer. So I can't change it because it's 100% correct. Then before we move on, how did we explain, or what do we understand if someone said a partially filled either D or F subshell? What comes into your mind when we say partially filled? Let's explain it in terms of transition element. So what did I say about that word? Yes, Joshua.
You said that the partially filled 3D element, it's when the D subshell is not filled to its maximum. For example, we know that 3D a D can be filled to 6, and when it is like 5, 4, or 3, then we say it is half filled.
Okay, thank you. So if I'm to share, this is a whiteboard. So when we talked about having a partial field, we said that if, for example, if it is a D block element, let me use a different color. Let me use a different color here. I can use red. So if it is a D subshell, it means that it's supposed to be carrying or having electrons ranging between 1 and 9. Remember, a D block element contains a D block shell contains a maximum of 10 electrons. So if it has 10, it is full, it is not partially filled. And again, if it has 0, it is also the same thing, because it's not containing any electron. And for an energy level to qualify to be called an energy level, it must be containing at least one electron. So that is why we are saying that our subshell must be partially filled. Or we can as well say that our partially filled energy level is neither full or half filled. So it is neither full nor half filled. That's what we mean. And we had elements ranging from scandium going to zinc. I hope we are together there. So today I want us to look at the characteristics of transition elements, the general ones. Each of their elements must contain at least one of these characteristics, or what we can call properties. So all of them must be having a variable oxidation state. What do I mean when I talk of variable? They are supposed to be having more than one oxidation state. In simple terms, we can call oxidation states like valencies. So we shall find that these elements, they have more than one oxidation state. Most of them. Take an example. If I have, let's say, manganese, not magnesium. So if I have manganese can have a valency or oxidation state of +2. It can have +3. It can have +4. It can have +5. It can have +6. It can have also +7. So you can see it has got more than one. How do we come up with these oxidation states? It is whenever transition element loses an electron, it forms a new oxidation state. This means that if we have +2 oxidation state, it means that manganese lost 2 electrons. If it is +3, then it lost 3 electrons. Just like how we had it in O level when we are looking at ion formation, that we form ions or positive ions after losing electrons, and we said the charge on the ion depends, or it is equal to the number of electrons lost. That is if you're dealing with metals. So that's what we have right now. So these transition elements, they form more than one oxidation state, as we shall see. And then again, Again, these transition elements or transition ions, they form colored compounds. Just like if you are to remember also in O level, whenever we had some practicals, especially those ones for testing the ions, at times the common example was when you have, for example, copper. Whenever you would get copper 2 ions, remember copper is a transition element. Whenever you get copper 2 ions, then maybe you add hydroxide ions. That is when they would tell us add sodium hydroxide dropwise until in excess. So here I would get hydroxide, and say that this is that was in then excess hydroxide or that addition excess ammonia solution. I'm not putting the physical states. So from it, a deep solution. So we are changing from having a pale blue precipitate, then to having a complex. To having a complex. A complex is also a compound. It is also a compound. So we'll get something of this kind. So this is a complex. So here we said it forms a deep blue precipitate. Rather a deep blue. So all these ones are colored. All these ones are colored. And if you have to look at also other if you have to look at other compounds of these transition elements, the same if we use the copper. If you look at copper carbonate, who can tell us the color of copper 2 carbonate? Who can tell us the color of copper 2 carbonate? You can raise up the hands. Copper 2 carbonate. We can have this is yes, Paul.
It's
I beg your pardon. Paul, I didn't hear. Paul, you can give us your answer again. I didn't hear what you said. Okay, Hillary.
I think it is blue.
It is blue. Okay. Any other? I don't think that is blue. Arthur?
Gray powder.
Gray powder. Thanks for trying. Henry?
Green.
Okay, Henry, thank you. So this one is green. It is green, pale green, not all that that deep green, but it is pale green. So you can see they have their compounds. Their compounds are colored. Their compounds are colored. So we shall look at more examples when we go to formation of colored compounds. So we shall explore or we shall expand these characteristics and we look at them individually. So formation of complexes, complex ions, like the way we looked at this one. The zinc also forms a complex, the other colorless solution that we used to see in O level. Then we shall explore more complexes and we look at their colors. Then also these transition elements, they have what we call catalytic activity. So here they can be the elements themselves or their compounds. So what do we mean when we say catalytic activity. It means that these compounds, rather these elements, can act as good catalysts, or they can act as catalysts. Like I said, the individual elements can be catalysts as well as their compounds. So can we name those catalysts which contain the transition elements? And if we can remember where, we can even state where we use them. To do that, you must be knowing all the transition elements we are talking about. If I want to do that, we have scandium, we have chromium, we have manganese, we have iron, we have titanium, we have vanadium, and so on. So which reactions or which catalysts do you know that contain transition metals? It can be a compound, or you can say an element. This and this can also act as in this kind of. Let's start with Beth. Yes, Beth.
Manganese for oxide in preparation of oxygen.
Okay, thank you. So she's saying that. Let me first get some space here. I can rub this so that we can get where to write these answers. What you should know is that we are writing history. We are writing history. You know, you can go somewhere and they ask you, "Are you ever given an answer in class?" You say yes. Remember when we are at school there, we don't get a chance of getting exposed to the world. So there we can lie, but here we can't lie, because we shall come and type in the name Beth and we see where she appears on YouTube or on net. So someone has said, Beth has said manganese for oxide in the preparation of oxide, in preparation of oxygen in the lab. Yes, Deborah.
Vanadium pentoxide in the contact process.
So we have vanadium pentaoxide, or what we call vanadium 5 oxide. It is used in contact process. Thank you. Ladies are taking over. Joshua, you've come to the rescue of the gentleman. Yes, Joshua.
In chemistry, we use zinc at a temperature of 150 degrees Celsius in hydrogenation.
Okay, we can use zinc. Do we use zinc or we use hydrogen? Rather, I think it is nickel. Anyway, but zinc can act as a catalyst. Okay, thank you for that. Another person. Let's remember all the organic reactions. There is where we have zinc and copper when they are connected. Yes, Shana.
Copper to sulfate in the preparation of hydrogen.
Copper to sulfate in the preparation of hydrogen. Thank you. People have answers only that they want to keep quiet. Shall I have brave? Brave, you have to show us that you're brave for sure. Yes, Emmanuel.
Iron in the preparation of benzene from ethane.
Okay, we have iron. And so on, and so on. Okay, Letitia, you are the last one. Letitia, I'm not hearing you. I don't know why. You can use the chat. Okay. So remember, that is what we meant when we say that these elements or their compounds can act as catalysts. You can see all of them contain a transition metal. Here we have manganese, here we have vanadium, we have zinc, we have copper, we have iron, and so on. Then lastly, we talk about paramagnetism. So this is the ability of these elements or these metals to be attracted by the magnets. To be attracted by the magnet. So all of them can be attracted by the magnet, but the attraction depends on the number of unpaired electrons in the 3D. Like we said at the beginning, that the chemistry of these transition elements depend on the number or depend on the 3D subshell. That is where the chemistry rotates. Then other shells come in. So that 3D determines most of the properties of these transition elements. Yes, Hilary?
Master.
Yes, please.
Some books give 7 properties. How?
Yes, some books give 7 properties. Maybe we missed them here. You can tell us and we see how to add them.
Formation of isomorphous compounds.
Formation of?
Isomorphous compounds and another word I can't pronounce it, but
we can say formation of interstitial, right?
Yes.
Interstitial.
Yes.
You help me with the spelling. Compounds, eh?
Yes, that is it.
So when you read that book, what does the book say about formation of interstitial compounds?
Small atoms, in particular, hydrogen, boron, carbon, and nitrogen, are able to fit in the lattices of transition metals, forming materials that are chemically similar to the metal, but having different physical properties from the metal.
Okay, basically, formation of interstitial compounds, at times the simple example you can give is the formation of alloys. That these elements are able to form alloys, just like how we have members. Let me first talk about this formation of interstitial compounds, then we go back to paramagnetism. So when we talk about this, it is like the formation of alloys, like how we can have let's say we can have, I'm looking for an alloy which contains, so we can have an alloy of manganese and copper. So we shall find that most of the alloys contain these elements, although they are always in smaller percentage. We have steel. Which alloy is in steel? Alloy, I think it is iron and carbon. Iron and carbon. That is for steel, and so on. So thank you for reminding me about this formation of the interstitial compounds. Okay. Then the other one we shall come to it. We shall come to it later when we go to the complex formation. That's when it fits in. Hilary, your hand is still up. I don't know whether you have something else to add on or you forgot to lower your hand. Okay. So when we go back to paramagnetism, I was saying that the extent of attraction depends on the number of electrons, of unpaired electrons in the 3D. Take an example. If I have my orbital here, it is supposed to be having 5 small boxes, 2, 3, 4, 5. So what happens is that if I have a 3D which has like 6 electrons, and I want to fill in these boxes. When you're filling these electrons, you first put 1 1, then after you come back and pair if you still have a balance. So like now I have 6, all of them they can face up like this. These are 2, 3, 4, 5, but we have 6, so we can also come and pair up here. So this element which has got 3d6, it has 4 unpaired electrons. And if I had another element, here I'm just being so brief because we shall look at it in detail. So I can have other 5 small boxes, 2, 3, 4, 5. Okay. Remember here I'm having 3, maybe you can say 3d8. So I put my electrons, I put 1. Remember I say first put 1 1, then after you come back and pair if there is any balance. Then 2, then 3, 4, 5, and I come back and now start pairing because I still have 3 more. 5, 6, 7, 8. So this one, so the first one with a 3d6, it has, we are saying it has 4 unpaired electrons. Then this one has got only 2 unpaired electrons. So the one which has more unpaired electrons, we shall find that it is more paramagnetic. So it can easily be attracted by the magnet, unlike the one which is having 2 unpaired electrons. So that property, or that property depends on how many unpaired electrons do you have. That's why when you look at, we shall find that if you have iron, if I have iron 3 and I also have iron 2, if I also have iron 2, so I have these 2 ions. So which one do you think will be more paramagnetic, or the one that will be easily be attracted by the magnet? So what you do here, first of all, for the beginners, you need to first write the electronic configuration of the neutral atom. Anybody who can remind me of the atomic number of iron? Is it 26, 24? How many? Someone to remind me. You can check on the periodic table. Let's be fast. We have a few minutes remaining. Yes, Emmanuel.
26.
Okay, thank you. 26. So we shall find that I'm going to use only the outermost. Okay, we can put the other one for argon like that we have it in our notes. So we can say argon here so that we can save time. This would be 3d 3d6 then for S2. That is how it will be. And again, when we are losing electrons, we start with the S going to the 3d. A reason, losing electrons from the S sub-energy level requires less energy compared to when we are losing electrons from the D sub-energy level. So that's why we lose electrons from the S going to the D. So when we are forming iron 3, how many electrons are we going to lose? Who can tell how will the configuration look? Remember this one remains. You can use a different color. Let me use blue. So we are now going to write the configuration for for iron 3. So I'll put argon. So you just need to tell me how many electrons I'll be having in the S or the 3D. So by show of hands, I'm also wondering whether it is only one person raising up the hand. Others are supervisors here. It seems the ladies are quiet. They are just saying gentlemen, the one they should go with in the future. Okay, Henry. Please, Henry, hurry up. Henry, GB, Henry.
39.
Sorry?
39.
39.
Yes.
Henry, I'm not getting you. Let's hear from Arthur.
3D5.
So we shall have 3D5. How about the S? Arthur, how about the S?
4S0.
Okay, so 4S is having 0, so there is no need of writing it if it has 0. Okay, thank you. Then for iron 2, let's put argon already. So that I'm just doing that to save some time. We look at other things. Yes, Tekino. This is a robot. Tekino.
Yes, teacher. 3D6.
Yes, saying Tekino. I don't know whether you are the musician from Nigeria. No, first wait.
Hello.
First wait. Hello.
3D6.
Yes, I'm hearing, but I want to first know your name.
Ainaman Joseph.
Ainaman Joseph.
Yes.
Okay. So you are saying that is
3D6.
3D6.
Yes.
How about the 4S?
No, the 2 electrons have been.
They have been removed.
Have been roasted.
Okay, thank you. So I want us now to have our boxes like these ones here. So for iron 3, we need 5 boxes. 1, 2, 3, 4. So then we need to put our ions. Remember I said that we first put 1, 1, then after you come back and pair if you have a balance. So we have 1, we have 2, we have 3, 4, 5. I'm seeing some 2 hands here. Yes, Hilary?
So what is a neutral ion?
A neutral ion is when it contains the same number of electrons and protons, so it is not charged. It has not lost any electron, so it is just charged. It is not charged. It has the same number of electrons and protons. That's what I mean by neutral ions, like the way we have it here. So here it had not done anything like losing an electron. So they are done. We have 5. Then we check. We check on this one. So now we are going for iron 2. So 1, 2, 3, 4, I think there are 5, okay? So we are having only 6, so we put 1, 2, 3, 4, 5, and then we come back and pair. So now from these ones we want to pick the one which is likely to be more paramagnetic. Yes, did you say you are an woman?
Yes, I'm a man.
Woman.
Yes,
Which
Joseph.
of these two
Joseph.
is okay, Joseph?
Yes.
Okay. Beth, which of these two is more paramagnetic? Beth, which of these two is paramagnetic? You can unmute.
Iron 2.
Iron 2. Sure. I think something is missing. Let's hear from Rodney. Rodney, how are you?
It's iron 3. I'm fine.
So
it's iron 3.
Iron 3. Reason? What could be your reason? Rodney? What could be your reason? Rodney, give us a reason. Why do you have to say it is iron 3? What if I said iron 2? Why is it iron 3?
Iron 2 has less. Hello?
Yes, please.
Hello?
Yes, I'm hearing.
Iron 2 has less. Iron 2 has less paired electrons compared to iron 3.
Okay, thank you. So members, here we are saying that in you can see most are unpaired. So here we have 5 unpaired electrons. Then here we are having only 4 unpaired electrons. And remember we said the more unpaired electrons, the more the magnet becomes paramagnetic. Any questions? Please, after giving your answer, it's good that you lower your hand so that you don't confuse us. So that if the new question comes in, then we can be able to know those who are going to give us the answers. So any questions? Yes, Joshua?
I have not understood iron between iron 2 and iron 3, which one is more paramagnetic?
Okay, we said that. Let me first remove these many colors, maybe they have confused you. We said that an element, a transition element or a transition ion, a transition metal ion is paramagnetic depending on how many unpaired electrons it contains. If it has many, then it is more paramagnetic. If it has less, then it is less paramagnetic. So we compared iron 3, which has all the 5 electrons unpaired, and also iron 2, which has only 4 unpaired electrons. So after comparing those two, we found that the one with more unpaired electrons becomes more paramagnetic than the one which has got less unpaired electrons. I don't know whether it is now fine. You can tell us, is it okay now?
Yeah, teacher, now I've got it.
All right. Any other question before we proceed? Because the thing is that if you understand them from here, when they are still listed, then when we go down, it will be much easier. We shall be getting them very fast. We shall just be adding to what we already know. So members, if you have any questions, you can use the chat, or you can even raise up your hand. In case I fail to pick you, then you can send your question via the chat. And I hope so far so good. Okay, so let me first remove all this. So let's look at them individually. We start with
Excuse me, teacher. Excuse me, teacher. Teacher, the chat has been disabled, and yet you're saying that you ask through the chat, yet it is disabled.
Sorry about that. Sorry about that. Sorry. Can use it. Thank you. So let's first which is oxidation state. We have looked at it. So here we define oxidation state, the charge left on the central atom. So here we are looking at a new one, central atom. What a central atom is: when atoms of the compounds have been ions. And oxidation state is the charge left okay. Sorry about that. That gone off. That we shall get to know what a atom is in this case, to know ions after being moved. But as per now, this is the definition of oxidation state. Definitions of oxidation is my opinion. Here we are saying determine the oxidation state of the chromium in a dichromate. So a dichromate, let me see. I think I should use a whiteboard. A dichromate, it is like this. That is a dichromate. We have the other side. So we want to determine the oxidation state of this dichromate, like the way we have it here. Like the way we have it here. In our dichromate, CR2, then O7, 2 minus. So I want to explain what all these mean. So here we are saying that the central atom is the chromium. So the central atom is the chromium. In this case, the central atom must always be a transition metal involved. The central atom is the chromium, the central atom we talked about here. So in this case, it's the chromium, because chromium now, it is the only transition metal in our dichromate. Then the overall charge, it is this one, -2. But remember, when we are writing a charge on an ion, the charge, the sign is always behind. So that's why we have 2 2 minus, but not minus 2. But this one can be interpreted as minus 2. I hope all of us know that. And then how do we determine the oxidation state? So we shall say that since we are determining the oxidation state of this element that we don't know, so we are looking for the oxidation state of chromium in our dichromate. So what shall we do? Here we are saying that let X be the charge on each chromium atom. Let X be the charge on each chromium atom. Instead of using X, you can use any other letter, but X is better. X or Y or Z. Those are the ones which are common. So we are going to assume that the charge on chromium, it is X for each atom of chromium. And we have 2 atoms. So that's why I just want to, expand this to see how we came up with the answer. So the charge would be, since there are 2 atoms, each atom is having an X charge. So we shall say 2 for 2 atoms, 10 times the charge for each chromium atom. Then plus the charge on the oxide ion. So this oxide ion. And the charge on the oxide ion, it is 2 minus. So we come and say there are 7 atoms of the oxide. So it is 7 into the charge on each oxide ion. So we say minus 2. Equaling to, we say the overall charge is minus 2. So whatever we are multiplying here are the charges. So we carry out mathematics. This one becomes 2x plus. So when I get positive 7 times minus 2 times minus 2, I'll get minus 14, equaling to the overall charge, which is minus 2. So when I compute, this would be 2x. Mathematically, if you have a minus times a positive, what do you get? You get a negative. So it would be minus 14, giving us minus 2. We continue. I want to show you all the steps. So this one will be 2x. When minus 14 crosses the equal signs to become the positive, so it will be 2x equaling to minus 2 plus 14. Then we shall get again 2x equaling to, so what we have on the right is the same as having 14 minus 2, which gives us 12. So we divide by 2 to make sure that we remain with only x on the left. So yeah, by 2. We cancel here by 1. So we remain with x, which give us, it is by 1, here by 6, which give us 6. But since we are calculating for the oxidation state, it must be having a charge. It must be having that sign, whether positive or a negative. So we come and add the positive, meaning the oxidation state is, it must be a charge. It must be a charge, and the charge must show the sign, either it is a negative charge or a positive charge, just like the way we define it. Is the charge left? Is the charge left? So x is now positive 6, meaning that the oxidation state of our central atom, which is chromium, it is 6. Anybody who is lost from there? Anybody who is lost, so that we can help? Okay, nobody. So I want us to finish this, then we call it a day. Okay, so members, we have managed to look at how we can check for the oxidation state. Can I have like 2 questions, then we call it a day? We need to learn how to manage the time. So any questions on this, then we call it a day. If there are no questions, then I'll assume that everyone has understood beyond any doubt. Any questions? Any questions? Okay. So if there are no questions, then let's have a closing prayer. Let's have a closing prayer. Yes, Gift. I'm seeing 2 hands. I don't know. Let's have a closing prayer there. Okay, let's have Shabai Brave give us a closing prayer. If you have any questions, you can ask, then you give us also a closing prayer. Yes, please.
I don't have any question. Father, we thank you for the gift of life. We thank you.
Yes, Brave, I'm not hearing the prayer.
Father, we thank you for the gift of life. We thank you for everything. We thank you for this day. We thank you for everything you have been able to do for us. We also thank you for these lessons that are so helpful to us. Amen.
Amen. So thank you so much for your patience today, and we meet next time. I'm going to send what we have covered today in the classroom, and let's make sure that we check it out. Okay. Have a good day.
Thank you.
Welcome.